Bismillahirrahmanirrahim. In the last lecture, we have studied the different type of singularities. Now, finally, we conclude the following. In the first one, in the neighborhood of an arbitrary point x is equal to a, every solution of 2 can be taken as y is equal to summation 0 to infinity a r x to x minus a to the power r. Second one, in the neighborhood of a regular singular point x is equal to a, the solution of the given differential equation 2 can be written as y is equal to r is equal to 0 to infinity summation a r x minus a to the power m plus r. Now the next topic is forms of series solution. Let us come back to how to solve in series the given second order differential equation. We assume the power series y is equal to summation r is equal to 0 to infinity a r x to the power r plus m as a solution of the given differential equation and substitute it in the differential equation to be solved. If our assumption is correct, then the resulting equation must be an identity in X. As such, the coefficients of various powers of X must be separately 0. This provides a sufficient number of equations to determine the unknown m, a naught, a1 up to. When the coefficients of the lowest degree term in X is equated to 0, the relation obtained is known as indicial equation as it determines the index m. Since the differential equation is also order of 2, its general equation is of the form y is equal to a y1x plus b y2x, where a and b are two arbitrary constants and y1, y2 are independent functions. The initial equation gives two values of m1 and m2 of the index m. Then, depending upon these values, we get the following cases of determining the general solution of the given differential equation of the second order. If x is equal to 0 is a regular singular point of the equation. Case 1, roots of the indicial equation are distinct but not differing by an integer, that is m1 is not equal to m2 and m1 minus m2 is non-integer. In this case, we get two independent solutions y1, y2 corresponding to each of the roots m1, m2. Thus, the general solution of the differential equation is y is equal to a y1 plus b y2. Case second, roots equal, that is m1 is equal to m2. In this case, both the solutions y1, y2 become identical, so we obtain only a particular solution. However, it can be shown that if Yxm denotes the series solution before setting m is equal to m1, then y2 is equal to del m del y over del m at m is equal to m1 or m2 is a solution of the given equation. Thus the general solution is given by y is equal to a yxm1 plus b del y over del m at m is equal to m1, where a and b are arbitrary constants. Case third, roots differing by an integer, that is m2 minus m1 is equal to integer. If alpha, beta, the roots of the initial equation, differ by an integer, alpha is greater than beta, the two solutions of the differential equation are y1 is equal to ym, m is equal to alpha, and y2 is equal to del over del m, m minus beta ym at m is equal to beta, where ym is series solution satisfying the relation. Now we are going to solve the problem. So example number 1, solve in series the differential equation 1 plus x square y double dash plus x y dash minus y is equal to 0. Solution: the given equation can be written as y double dash plus x over 1 plus x square y dash minus 1 by 1 plus x square y is equal to 0. Equation number 1. Here x is equal to 0 is an ordinary point, therefore we can assume the solution in power series as y is equal to summation of r is equal to 0 to infinity ar x to the power r. Equation number 2. Now substituting 2 in equation 1, we get 1 plus x square summation r is equal to 2 to infinity r minus 1 ar x to the power r minus 2 plus x r is equal x summation r is equal to 1 to infinity r x to the power r minus 1 minus summation r is equal to 0 to infinity ar x to the power r. Equation number r is equal to 0 implies summation r is equal to 2 to infinity r minus 1 ar x to the power r minus 2 plus summation r is equal to 0 to infinity r minus 1 ar x to the power r plus summation r is equal to 0 to infinity ar x to the power r minus r is equal to 0 to infinity ar x to the power r, which is equal to 0, or summation r is equal to 2 to infinity r minus 1 ar x to the power r minus 2 plus summation r is equal to 0 to infinity r minus 1 r plus 1 ar x to the power r, which is equal to 0, or summation r is equal to 2 to infinity r minus 1 ar x to the power r minus 2 minus of a naught plus r is equal to 2 to infinity r minus 1 r plus 1 ar x to the power r is equal to 0. Equation number 3. Equating to 0 the coefficients of terms of various powers of x in equation 3, we get 2 into 1 a2 minus a naught is equal to 0, or a2 is equal to 1 by 2 a naught, comma 3 into 2 a3 is equal to 0 implies a3 is equal to 0, and r plus 2 r plus 1 ar plus 2 plus r minus 1 r plus 1 ar is equal to 0, recurrence relation where r is equal to 2, 3 up to infinity implies a3 is equal to 5, a5 is equal to a7 is equal to 0. I mean total odd numbers will be 0, and ar plus 2 is equal to minus of r minus 1 ar over r plus 2, where r is equal to 2, 3, 4 up to infinity. Hence, a4 is equal to minus 1 by 4, a2 is equal to minus of a0 by 8. A6 is equal to minus 3 by 6, a0, a4 is equal to a0 by 16 equation up to, and so on. Substituting these values of the coefficients into, we get y is equal to a0 plus a1x plus a2x square plus a4x to the power 4 plus a6x to the power 6 plus and so on is equal to a1x plus a0 taking common within the bracket 1 plus x square by 2 minus x to the power 4 by 8 plus x to the power 6 by 16 and so on. As this solution contains two arbitrary constants a0, a1, it represents the general solution of the given differential equation. Now we are going to solve the next example, which states that solve in series the differential equation 2x 1 minus x d2y over dx2 plus 1 minus x dy by dx plus 3y is equal to 0. Solution: the given equation can be written as d2y over dx2 plus 1 by 2x dy by dx plus 3 by 2x x minus 1 into y is equal to 0. Here px is equal to 1 by 2x and qx is equal to 3 by 2x x minus 1. It is not regular at x is equal to 0, but xpx and x square qx are regular at x is equal to 0. Therefore x is equal to 0 is a regular point for the given differential equation. Hence we assume its solution is y is equal to summation r is equal to 0 to infinity ar x to the power r plus m. Therefore dy by dx is equal to summation r is equal to 0 to infinity r plus m ar x to the power r plus m minus 1, and d2y over dx2 is equal to summation r is equal to 0 to infinity r plus m minus 1 ar x to the power r plus m minus 2. Substituting these values in the given differential equation, we get 2x 1 minus x summation r is equal to 0 to infinity m plus r minus 1 ar x to the power m plus r minus 1 plus 1 minus x r is equal to 0 to infinity m plus r x to the power m plus r minus 1 plus 3 summation r is equal to 0 to infinity ar x to the power m plus r is equal to 0. After simplifying, we get summation r is equal to 0 to infinity m plus r 2m plus 2r minus 1 ar x to the power m plus r minus 1 minus summation r is equal to 0 to infinity m plus r plus 1 2m plus 2r minus 3 ar x to the power m plus r is equal to 0. Equation number 3. Equating to 0 the coefficient of the lowest degree term in x, we get the initial equation to m minus 1 a naught is equal to 0 implies m is equal to 0 1 by 2 since a naught is not equal to 0. Now equating to 0 the coefficient of x to the power m plus r in equation 3, we get the recurrence relation as m plus r plus 1 2m plus 2r plus 1 ar plus 1 minus m plus r plus 1 2m plus 2r minus 3 ar is equal to 0. Or ar plus 1 is equal to 2m plus 2r minus 3 over 2m plus 2r plus 1 ar, comma r is equal to 0 1 2 up to and so on. Equation number 4. Now taking m is equal to 0, we get ar plus 1 is equal to 2r minus 3 over 2r plus 1 ar, where r is equal to 0 1 2 up to. Therefore a1 is equal to minus of 3 a naught, a2 is equal to minus 1 by 3 a1, a3 is equal to 1 by 5, a2 is equal to a naught by 5, a4 is equal to 3 by 7 a3, so a naught by 7 into 5 a naught, a5 is equal to 5 by 9 a4 is equal to 3 by 7 into 9 a naught, and so on. Therefore the first solution may be written as y1 is equal to a naught 1 minus 3x plus 3 by 1 into 3 x square plus 3 by 3 into 5 x cube plus 3 by 5 into 7 x to the power 4, and so on. Next, taking m is equal to half in equation 4, we get ar plus 1 is equal to 2r minus 2 divided by 2r plus 2 ar r minus 1 over r plus 1 ar. Hence a1 is equal to minus of a naught, a2 is equal to 0, a3 is equal to 0. So all the terms except the first two into are 0, and hence the second solution is y2 is equal to a naught x to the power half 1 minus x, and thus the general solution is y is equal to a y1 plus b y2, where a and b are arbitrary constants.